Welcome back to the channel. This is part 2 of a lesson idea about linear regression involving a topic for biology classrooms, and we're looking at brain weight or brain mass and head volume. So if you haven't seen it, check out part 1 where I talk about the data setup and assessment to make sure that our assumptions are satisfied. This is part 2 where we start to look at the linear model that we're going to construct. So let's go ahead and dive in. So we have our data set up the way that we want them to be, so they're ready to go for analysis. So we need to construct a linear model. And in this is the LM function, which stands for linear model. And to do this, we need to give it our variables and then identify the data. So I have my data set just called main, and then the notation here for the model itself, we're really just looking at these two variables. So we're looking at brain mass, and that's going to be our output. And then there's a little tilde, and then there's the head volume, which is our input. So first thing I want to do with this is to do a short summary of this model. This gives us a lot of information to look at. And what we can see first, there's the model itself listed at the top. And then the important part here, we can see the intercept value and the estimate of that input value. So that's the actual set of coefficients for our model. And then another important part here is the R-squared value and the p-value, and we'll take a look at those next. So for our assumptions, we looked visually at the linear relationship when we saw a scatter plot in part 1. We also looked at the correlation, which was high. It was over 0.8. So there was a positive, relatively strong relationship shown. But now we can use the model itself to do an assessment of how linear, the extent to which this relationship is linear. And the R-squared value is how you can do that. Now, in this case, it's in the summary, but what I did in this small part here where I checked the fit is I'm taking the summary of our linear model and I'm extracting this R-squared value from it with this $r.squared portion after that. Because it's a fraction written as a decimal, I'm multiplying it by 100 and then rounding it to a couple places. And then I'm making this statement. So this is just, it's an unnecessary thing, but it's nice if you wanted a nice statement to sort of summarize this. So the statement is now, this model explains approximately 67.89% of the variation in brain weight due to head volume. Now, I should say brain mass. That's a mistake on my part. But this is just an example of how you can take part of your linear model and turn it into a complete statement. So in the interest of a reproducible report, if you had a statement in your report that relied on data that might change if you had a different, say, a different data source, this would be a nice way to keep that up to date because it's being populated by the model. So the next thing I wanted to do after re-examining that linearity issue is to look for the variance. Now, we didn't do this before in part 1, but using the model, we can look at variance and see if that assumption is also satisfied. And a way that you can do that is to plot the residuals. And so in this particular plot, what you're looking for is random scattering. You don't really want to see a strong pattern here. So on the left, there's a 0, and that line, if you can imagine, goes right through the middle. You'd like to see points distributed above and below this line, and then kind of scattered around in a sort of random way. And we see that, so that's a good sign. And then another thing you can do is look at what's called a QQ plot, and that's sort of a visual test of normality. So again, we did a test previously to look at normality, but once you have your model, you can do this as a visual check. And this particular plot produces essentially a string of data points that should end up on a line. So here we see that most of these data points do in fact line up, and so that's a good indicator that everything's okay. And then another way you can look at normality is to plot the density of the residuals. And so again, this is a relatively straightforward thing to do here with the short command here. But the output is going to be a curve, and it should look approximately like the normal distribution. And in this case, that's what we see. It looks okay. Now we can move on to check out the model in the context of our data points. So in this next one, this is again just base R graphics, but we plot the head volume and the brain mass, and then we add what's called an AB line, and we just use our linear model to sort of tell it what it needs to draw. And then I'm giving it a blue color just to make it stand out a little bit here. But what we can see is that our model passes right through the data points as expected, and it looks pretty good. Now, if you wanted to know the actual equation behind that model, we have this linear equation. You may hear it as y equals mx plus b, or beta 1x plus beta naught or something. So what you can do here is use your linear model and extract the coefficients from it. So you just use that $sign to get at the coefficients within your linear model. Now, below in this code right here, I'm just using some text tricks to pull that out and write the values in a complete statement. So what we end up with here is y equals 317.71 plus 0.26x. And so that tells us that the x here in this case is our input, and that's the head volume. So brain weight is equal to 0.26 times head volume plus 317 or so. And so that is something that you could then use to predict other values. So if you know the head volume, you could predict the brain weight from it. And so what we can do here in this next step is to generate a new test, a new made up set of values here. And so this is just a little tibble with one column called head volume, and I gave it some values. These are not from any particular place, but if you're doing this as a lesson, you might want to try and figure out the head volume of someone with a measuring tape, and then you could plug that value in and then get a prediction on what their brain might weigh. And so that really depends on the quality of this model and whether or not it applies to those individuals, but that's another discussion. But here we can also do the prediction with the predict function. So we just tell it what model we're using, which is LM as we called it, and then we're using the data set here that contains our test values, and then that gives us some prediction. So the way you could read that is if the head volume is about 3.2 liters, then the brain mass would be about 1.16 kilograms. That's the end of part 2. And in part 3, we're going to be looking at that data visualization and trying to improve it so it gets ready for publication. So stay tuned. If you like this video, make sure you hit subscribe to the channel and give this video a thumbs up. And I'll see you next time. Thanks.